Hello, my name is Rob Boss and we're going to paint happy trees. But first, let's do some physics problems. Our first problem is the following event will be used for questions 1 through 5. That part's not important. The important part is John Jonathan Johnson decides he wants to listen to his favorite song. He puts a CD onto a CD player and the CD starts up at a constant angular acceleration of 20 radians per second squared. So let's write that down. 20 radians per second squared. The CD then eventually reaches a constant angular velocity of 535 revolutions per minute. This is going to be our final angular velocity, and that's 535 revolutions per minute. And that's when the song starts. The song lasts for 2 minutes, and then John turns off his CD player. Then takes the CD 4.3 seconds to slow down to its constant velocity. So our first question is, how long will it take for the song to start? So the only important bits of this question that we need to use is going to be the beginning parts, so that the constant angular acceleration is 20 radians per second squared, and the CD then eventually reaches a constant angular velocity of 535 revolutions per second, which is this one. This is going to be our final angular velocity. So that means our initial angular velocity we already know to be 0. And we also know that it has to be converted to radians per second. So we have to multiply 535 by 2 pi over 60, because 2 pi times revolutions gives you radians, pi, and then you divide the whole thing by 60. So now we have to find the time it takes to start up the song. So we can use our first angular kinematic equation, which is the final angular velocity is equal to the initial angular velocity, rotational velocity, whatever, you get it, plus the angular acceleration times the time. So we know that 56 radians per second squared is equal to 0 plus the angular acceleration of 20 times time t. So now I just gotta solve for t. And 0 is 0, so bye-bye 0. So 20t. What is 56 divided by 20? 2.8 seconds. Which is an answer choice. Go us. I'm going to tag out. Second question.
Hey guys, I'm Ross Bob, and we're going to paint some happy trees. But first, we're going to do some physics. So, let's talk about number 9 on our review, in which a merry-go-round is powered by a rocket creating a torque of 2,000 Newton times meters, causing the ride to accelerate at 500 radians per second squared. What is the ride's moment of inertia, assuming it starts accelerating from rest? Well, let's write down what information we have, shall we? So we have a torque of 2,000 Newton meters. And we have an acceleration of 500 radians per second squared. Right, so first what we gotta do is set up the equation for torque, which is torque is equal to IA. So we can calculate the moment of inertia by setting torque equal to 2,000 Newton meters and then setting acceleration equal to 500 radians and then solving for I. So let's work that out. We have 2,000 Newton meters is equal to I 500 radians per second squared. Then we divide by 500, not 5,000, 500 and then we get I is equal to 4 kilograms times meters squared. And this is our answer.
Hello, my name is Ob Ross, and we're gonna paint some happy trees. But first, let's do a physics problem. We're gonna do number 7 from our physics review. And I'm a blind boy. This joke was a bad joke. In the picture above, what is the torque exerted by the 23 Newton force? Now I'm gonna do you guys a favor, and by you guys, I mean one person watching this video. We're gonna draw ourselves a little door. Look at how cute that door is, but you can't see it from down there. I do that on purpose. So let's do it a little bit bigger. Here we go. Look at that door. So nice. I bet there's all kinds of mysterious things on the other side of that door, but I'll never find out. 23 newtons is exerted at an angle of 30 degrees. And it is at a radius of 1.5 meters away from the hinge point, which is the rotational axis spinny bit. And the question is asking, what is the torque exerted by that 23 newtons? So, torque equals big old question mark. So, to solve this particular question, we have to find the vertical bit of the force exerted at the angle of 30 degrees. 30, just 30. This hat's a dumb hat. Let's see. So, if I wrote down the equation of torque equals force times the radius times the sine of the angle theta, we'll get our answer. So, torque is equal to the force, which is 23 newtons, times our radius of 1.5 meters, times the sine of the angle 30, we should get our final answer. Make sure your calculators are in degrees, folks. Of a negative 17.25 newtons times meters. And I really, really hope I did that equation right. Because also, don't forget it's negative because this motion right here, this spinny bit, is going clockwise because clocks tell time that way, and that's negative. Bad. This is the part where my audience claps, but there's no one here.
Hey guys, my name is Sorba, and we're gonna paint some happy trees. But first, let's do some physics, because that's more important. So let's talk about question number 12, in which a ball spinning at 20 radians per second has a moment of inertia of 2 kilograms times meters squared. Then another ball that is perfectly inside the first ball and has a moment of inertia of 3 kilograms times meters squared is placed on top of the spinning ball. How fast do the combined balls now spin? Well, this is about angular momentum and how it's conserved. So we know that L1, or not L1, L naught is going to equal L final. And the equation for angular momentum is moment of inertia times its angular velocity. So we can say moment of inertia initial times angular velocity initial is going to be equal to moment of inertia initial plus, or no, not that, moment of inertia final times angular velocity final. So our numbers are going to be 20 radians per second, and that ball has a moment of inertia of 2 kilograms times meters squared is equal to 2 plus 3 kilograms times meters squared. Now the reason that you add them is because now they have a combined moment of inertia, because now the two are spinning with each other, or not spinning with each other, but they're combined now, so they have to, they have to follow the rules of angular momentum. Now, we need to calculate its final angular velocity. So we do 40 is equal to 5w final. And then we just solve for w final. And then we get 8 radians per second. And this is our answer, which is an answer on our review. So yay! Now let's paint some happy
Whoa,
trees.
we're not there yet.
We're not there yet.
My assistant Sorba.
Oh.
We gotta end this dang video. Oh hi! My name is Thor Boss, and I was just eating this pizza. Sure tastes like plastic. Ha ha ha! Who needs that? The important part is that we're gonna do some happy trees. And by do, I mean paint. And by paint, I mean do them later, because physics is happening right now and it's more important. So we got ourselves a conceptual question, and we've got a boy here who's trying to balance an axe on his finger. Now, it's perfectly balanced, so I don't know, I'm gonna draw myself a finger. Oh man, that was a good finger. And then I'm gonna draw myself an axe. Whoa, Paul Bunyan, where'd you get that from? A store, sure did. Alright, so now I got myself a finger and an axe. And this is not accurate, even a little bit. And it kind of looks like the dude's finger got bit by a real big rat. So, the answer choices for this particular question are, they believe that the long handle weighs more. Oh, I'm sorry. The question is that which side weighs more, and the answer choices are either this side weighs more or this side weighs more, or they weigh the same. But I'm here to let you know a little secret. The correct answer is that this side weighs just a little bit more, because if you work out using the thing, oh no, okay. If you work out the problem using yourself a little bit of torque going on here, because we're trying to find equilibrium. So the torque of this weight of the axe has to equal the torque of this weight of the axe. However, their masses don't necessarily have to be the same, because this side's got a whole big old heavy bit, and this side is like longer, and the thumb, finger, what have you, is not perfectly in the middle of the axe. It's a little bit more to this side, so that this more bar thing balances out, because that's the center of mass. I'm pretty sure that's how that works. Okay, so assuming this mass of the axe is, let's say, actually that's not how we're going to do this. Let's just say this is M1, and this is M2. This is the third bar. Now let's say the radius for this is equal to 1, and this is equal to 2. Cool beans. So, torque you can find by multiplying the force, which is just your mass, times your acceleration due to gravity, which is 10, times your radius, which is 1 for the first torque, and then the second torque is equal to mass 2 times 10 times your radius of 2, and that gives you an answer. Big ol' answer. But these have to equal each other. So this first torque is going to equal 20 M2, and it's going to be going, yeah, it's gonna go down. So that means clockwise, because clocks go this way, negative. Bad. It's a negative 20, negative torque. And it's in 20 times the second mass. And it has to equal, or the magnitudes have to equal the other torque, which is 10 times the mass of 1. So if you're going to set up the torques to be equal, these two torques here, or the magnitudes, then you have, say, 20 M2 is equal to 10m1, and you divide, and you got yourself a proportion. So we got 2m2 is m1, which means that the mass of this axe part is twice that of the mass of the handle part. So the answer is the side with the head of the axe, the pointy bit. Shing, shing. Look at that sparkle. Wait a minute. Look at that sparkle.
Hi guys, my name is Bob Rob. And we're gonna paint some happy trees. But first, let's do some physics, because physics. So let's talk about question number 15, in which a windmill has a speed of 20 revolutions per minute, and it has a moment of inertia of 4 kilograms times meters squared. Then, what is its kinetic energy? Well, this is obviously a rotational kinetic energy problem, so let's write down the equation of rotational kinetic energy, which is K is equal to 1/2 I W squared. Okay, that is that. Now, let's plug in our information that we have. So we have K is equal to 1/2 4 kilograms times meters squared. And we also have 20 revolutions per minute. But wait, that's in revolutions per minute. So we got to convert that to radians per second. So let's do 20 revolutions times 2 pi divided by 60, because there's 60 seconds in a minute. So if we do our calculation, it's real bad, real bad.
Bo Robs!
I'm sorry. Okay, so I got my work. Oh, that took me a while. So we have, from my little cheat sheet here, that it comes out to about 2.1 squared. Okay, so then whenever we square that out, we get about 4.3-ish. Alright, no, I lied again. 4.4-ish times 2, because 1/2 of 4 is 2, is equal to K. Now, we get 8.8 joules for K. And that is the answer.